There. So today we're going to talk about force fields for classical molecular dynamic simulations of biomolecules, which is what you have been doing and what you're supposed to learn this week, at least the basic of it. And so the reason we talk about this is that so you need certain files to go into the NAMD engine to get your simulation started. And then you run your simulation, and then comes the analysis part, the discovery part, which is something you should do on your own. So, but those files, if one of those files is missing because you have a particular ligand or a drug or a modified residue, something that doesn't exist in the standard force field, then if you don't know how to do those and come up with parameters and topology for those, that's the end of the project. There's nothing you can do. And that becomes usually very often a problem. So that's why we would like to look at these files a little bit in more detail. So it's going to be, in a way, might sound boring to look at these files, but I try to combine this with some practical tips about how to set up the simulation, PK calculation, or some practical considerations that might be useful when you are putting together this molecular simulation. So you have seen QuickMD. QuickMD helps a lot with many of the steps that I will talk about. Maybe I will even overlap. I don't know to what degree you guys covered the calculation. It's not much. Okay.
We mentioned that we need to perform this calculation.
Okay, great. Good. So the idea again is to know, what is a topology and a structure file, what are things in there. Plus, if you know this, then you can easily go into those files and change something, modify something. It becomes very powerful. If you want to change the mass of one of the atoms in the molecular system to test a hypothesis, then there is only one number that you need to check and change in these files. It's good to know where all these numbers that go into your calculations come from, and if you need to change them, where to find them and how to change them, and most importantly, to be able to make topology file and develop parameters for unknown molecules. For proteins, for amino acids, standard amino acids, we have a standard force field. For lipids, for DNA bases, and some basic molecular systems and cofactors, we have them, but for many drugs, we don't have them. So that's the idea of today. So I'm hoping after today you feel much more confident and comfortable working with these files. So that's what we have been discussing. So classical molecular dynamics, you start with the setup coordinates, so positions coming from the crystal structure, from your favorite molecular modeling program, and then you assign initial velocities to them based on Maxwell-Boltzmann distribution to achieve a particular temperature at which you want to simulate the system. And then from that point on, it's just keep going. So calculate the new positions, how far these guys move in 1 femtosecond according to these velocities. And at that point, you stop. We calculate the forces, how they are interacting with the environment based on the rules that you have dictated, and then do this again and again and again and again. So, talking about the forces, so let's go back to the potential energy function, the derivative of which is the force. It's easier to discuss this non-vector form instead of talking about forces. So the potential energy, so now if you have a bunch of atoms, particles in space, no bonds between them, no charges. You have the basic van der Waals interaction between all these atoms. This comes from dipole-induced dipole interaction. So any atom might get polarized at some point, and that dipole might induce a dipole to its neighbor, and they start attracting each other to some degree. So that results in some attraction between any pairs of uncharged atoms because of the electronic flexibility of the electrons. And then, but if you bring them too close to each other, then you start actually bumping them into each other, and they start repelling each other because of simple steric reasons. And then you're going to have a repulsive part of this interaction. So we call this a Lennard-Jones kind of potential. This is one way of describing van der Waals interactions. So you might see other forms. This is known as 612 potential. You might have seen 510 or other things, or there might be other ways to describe this. So what goes in here, you have the distance between the atoms, Rij, I and J refer to the two atoms. All of the potentials we're going to describe are pair potential. At the end of the day, you'll end up with two forces or multiple forces balancing each other. Ij is the distance between Rij is the distance between them, and then you have two parameters. R mean is the sort of the distance or the radius. R mean Ij is the distance at which you have the minimum energy. So these potentials look like something like this. So this distance is the R mean value at which you have the minimum of the energy. And this epsilon Ij determines the depth of this potential energy. So these two parameters are something you have to specify for each atom pair, carbon sp3 and nitrogen sp2, for example. And then I need to specify these two parameters. So now, if these are charged, then in addition to van der Waals and Lennard-Jones potential, we need to have charge-charge interaction. That's a simple Coulomb interaction, potential energy function that we have here. So Qi, Qj are the partial atomic charges. That's the terminology I start to use. Partial atomic charges. They're not always integer numbers. So it could be partial charges that you could argue what it means. So that somehow we assign a partial charge to each atom in the system, and based on that and the distance between pairs of atoms, you're calculating the attraction or repulsion or the potential energy of the state, and based on that, you can calculate the force. It tells you whether they are attracting each other or repelling each other. So these are the two types of non-bonded interactions, and as I pointed out already on Monday, the problem is that what makes it really, really complicated is that you are dealing with molecular systems. And now you have to define a large number of new rules, how CC interact with each other, how this bond behaves, etc., etc. So for every molecular system, then you have to start to define the topology. We refer to this as the structure. Structure doesn't necessarily mean the coordinate, the Cartesian coordinate. We refer to this as the structure, the topology of the system, what is bound to what. You have to define all these bonds, all these bond angles, all these dihedral angles. And of course, for each of these internal coordinates, now we need to have parameters. What is the functional form that we're going to use to describe these internal coordinates, and then what is how strong these springs are, or how difficult it is for the bond to rotate, etc., etc. So a large part of the topology and parameter files that you are using in this business goes into just defining these things. And if you want to develop a set of parameters for your new drug, then you have to go through this. So this is a tryptophan residue shown here as an example, but you might have something that doesn't exist in the standard force field, and you need to develop all these information and put them in the right format, in the right file. So these are the four types of internal coordinates or bonded parameters or that are used in biomolecular simulations. So bonds are described as springs. Angles are also described by harmonic potential, simple springs, which means for them you have to define a equilibrium value at which the bond is happy, lowest energy, and then the force constant of that spring, meaning that how easy it is for the bond to bend, how easy it is for the bond angle to bend or for the bond to stretch. For dihedrals and improper dihedrals, these are proper dihedral angles defined as 4 consecutive atoms in the system. I have to define all the atoms involved, all the atom types. We have atom names. This could be your initial. You just put them there. They don't have any chemistry, any chemical meaning. And we have atom types. And atom types determine the parameters that are used for these atoms in the parameter file. So you have to define atom types for each of these atoms, and then you define actually dihedral potential, which is a cosine function, a periodic function allowing the dihedral angle to rotate. Improper dihedral angles are again dihedral angles, two planes, dihedral. These are also two plane potentials, but these are not periodic because here the concept of rotation doesn't exist. You're trying to confine and constrain this center to a particular shape. In this example, it's a pyramid, so you want to keep the pyramidal shape, but most often you use that to keep planar centers. Most of the sp2 carbons and nitrogens that you have in your amino acids usually have additional improper angles defined for them. An example of the potential energy function that we have, so as a function of the coordinates. And again, you will have all the bonds here for all of them. First of all, you have to determine, and the code cannot do that for you. You have to tell the program what is connected to what. All the bonds should be defined. And this is going into your PSF file that we will do that. And for each bond, you need to have force constant, how stiff that spring is, and then equilibrium value. And then the RI, the actual bond distance, will be calculated from your simulation or start, when you start from your PD. The same for all the angles, all should be defined, all three atoms involved in each angle are defined, and for each angle they have again force constant, equilibrium value, allowing you to define this harmonic potential. So that would be your bending motion here, the stretching here. And then for dihedrals, again, we define all the dihedrals. You see there's a lot of redundancy here. So we have too many internal coordinates involved in this business. We define all the possible dihedral angles, and then for each of them, we need to calculate the force constant here for this cosine function, and two other parameters. One is the phase, and then the other one is the periodicity. How many times you come up, go through the same energy when you rotate 2 pi or 360 degrees. So where is the position of the minimum and maximum, or minimum or maximum in that potential? And then as we discussed for the non-bounded part of the potential, we have the Lennard-Jones interaction. So now you see a different way. Now you're talking about sigma instead of R mean. So that's essentially the same thing. Don't have to worry about that, but we need two parameters, epsilon ij for each pair, and sigma ij, the optimal distance. And then for the charge part, we need the qi and qj. So now the question is where these guys come from, and we're going to work with, show you those. This is supposed to animate, unfortunately it doesn't. We show you the stretching motion here, the bending motion here, and the rotation of this methyl group, which is a sort of simple thing and easy thing to see in the simulation. So in terms of bonds, just to give you some idea about the magnitude of these numbers, so we have single, double, and triple bond here. So the bonds, if you're dealing with sp3, sp2, sp carbons here, this is, we are not going to tell the program that they have this hybridization. The only thing we do, we know that the single bond is longer and is weaker compared to a double bond and compared to a triple bond. So the only thing we do, we define these as different atom types. And then after that, we say if atom type 1 is connected to atom type 1, then use this force constant and this equilibrium value. That would give you this shallowest form of the energy here. So if you now change the atom type to 3 and 3 here, suddenly you have a higher force constant and a shorter bond distance, giving you this yellow curve, sort of more steep potential here. And that's all we do. We just change these two numbers in the potential for a pair of atom types, and then it's going to be behaving like a triple bond. They're all simple springs. There is nothing special about them. So these are, by the way, very stiff, even though I'm talking about weak and strong and stronger. Even this one is pretty stiff. These are very high frequency motions and very large values. A simple deviation from from many of these can actually increase the energy of the system by several tens of kilocalories. So these are very stiff, and they just move very, very little in your simulations based on the KT energy, half a kilocalorie energy that is available. So this is another example of a dihedral potential, and here again pointing out what happens when you play with these three parameters: force constant, periodicity, and phase. Actually, in this case, the phase is the same for all of them, so we are just changing the force constant and periodicity here. The first example has a periodicity of 1, so it just goes 1 maximum, 1 minimum over 2 pi. But a high force constant, that's a difficult bomb to rotate. We can actually use that to fix it at a possible angle. The second example, the purple one, has a periodicity of 2, could be a double bond, for example, and it has a force constant that is half. We're using 5 here. That results in a 10 kilocalorie per mole energy barrier because of this one value here. So the cosine function, as you know, changes from -1 to +1. Just to make everything positive, we add this 1 here. So now this term here is going to change between 0 and 2 times your force constant. So that's why you see it change from 0 to 10. You calculate your barrier quantum mechanically, you have to divide it by 2 before stick it into this position. And then the third example could be the rotation of the methyl group that we saw. Very low barrier, easy to rotate, and it has a periodicity of 3 times. You see the same energy. So this is just defining this, some sort of housekeeping, more keeping track of the all the bonds, angles, and the dihedral angles, and just providing the right atom types and right parameters for these interactions. For non-bounded parts, again, we have the charges. We call them partial atomic charges. And there is a, let's see if I come back to this later. Yeah, I think I do. So. Okay. So partial atomic charges, you can also specify the dielectric constant. Let's say it's the simplest way of introducing your solvent if you don't have it explicitly in your simulation. So you can put a dielectric constant representing your solvent here. There is a command in NAMD allowing you to specify a dielectric constant. For explicit solvent simulations, obviously we don't use that because your solvent is supposed to do that explicitly. Yes?
Can it be changed for specific pairs of atoms, or it's just general?
Say it again?
Can the electric constant be changed for specific pairs of atoms, or it's...
No, because I don't know what kind of physics you want to have in which only 2 kinds of atoms are affected by dielectric effect, which is a macroscopic.
From this measurement that the electric constant within a protein can actually vary a lot depending on the environment. So can you implement that?
That's very hard. In fact, actually, that's a major problem with implicit solvent kind of description. So really defining the area in which you have the dielectric constant of 2, you can define it in a particular area. You say in this area, this is the dielectric. In what is water area, what is protein area. And as you know, protein, we have to use one number. So we just say 10 or 20 or 4 or whatever. So, but as you know, again, dielectric is a bulk effect. So it's really not a good idea to try to specify it in a 5 angstrom region between 2 charged amino acids, because it's much easier to bring in the electric field and electrostatic effects explicitly for every atom or even electrons included. So it's very hard to do that, and that's the major disadvantage of implicit or major uncertain part of using implicit solvent. So now, in NAMD, we cannot do it. There's just one number that affects all the charge-charge interactions. So there are other ways to tune the interaction between particular atom types. You can do that using the so-called NB fix, non-bounded fix. So we use the similar form of the potential, and we define additional terms like this to make them more attractive or more repulsive, because maybe you realize there are some issues with the original potential. Or maybe you want to artificially tune these and make them more repulsive and see what happens. So that comes at the end of the parameter file. That's a very useful way of, like, for example, let's say I know that sodium, that was one of the original examples. I know that potassium ions, when they interact with carbonyl groups in my protein, you have a standard kind of interaction between potassium and oxygen. That's the standard part. But I know that for a particular part of my protein, when they come too close, this potential is not quite right. Maybe they get too close to each other according to this potential. I want to separate them a little bit. Then I'm going to introduce additional NB fixed terms there to push them apart a little bit and to prevent them from interacting too strongly, which I know from my previous standard simulation. So those are very powerful ways of adjusting quickly some of the interactions that you have. Okay, Leonard-Jones, again, epsilon, our mean, and we will see how it works. We use actually combining rules for non-bonded interactions. So we will see for bonded interactions, we define every possible combination of 2 or 3 or 4 atom types. So that you have to, becomes a little bit tedious. For the non-bonded part, because it's, these are all pair interactions and pretty simple, so we are going to define epsilon and R mean for individual atoms, I or J. And then we are going to use a combining rule to get the pair parameters. So the R mean I plus R mean J, or in some formulations, the average of these two divided by 2 would give you the pair parameter for the distance. And then epsilon I and epsilon J, when you have them, you look at the square root of the product, the geometrical average, to get the epsilon value that you need for any pair interactions. So electrostatic interactions are considered long range because they die with R. So whereas these guys, R to the 6 and R to the 12, this is really, really short range. It only acts at very short distances, especially the repulsive part. One thing that is special, I'm going to come back to this electrostatic later, even though the van der Waals, the Leonard-Jones potential, is pretty weak and short distance, one thing you need to remember is that at long distances, so this part is going to go away almost completely, so you're going to be always attractive at long distance. Any pair of atoms are going to attract each other. So what that means is that even though these are pretty weak interactions, but you might have these interactions between many, many of the atoms. In the electrostatic part, some atoms with like charges repel each other, some attract each other, it might balance out. But for these guys at long distances, they are all attractive. Let's say you have 2 planes, 2 membranes, things of that sort actually can really add up to strong interactions even at long distances. So that's something that can give you to some degree, the ring-ring interaction that you might have, sugar, aromatic interactions, these kind of things usually come from this term here. So, but this one also dies with R to the 6. So now this guy, you have 1 over R, and that's why we consider it the long-range non-bonded interaction. That again, it might be repulsive or attractive depending on the charge types, and that's why this was one of the first things that people try to improve better. Because as you will see, we have to use a cutoff. So for any of these non-bonded interactions, if you want to include all pairs in your calculation, then you have to calculate n squared, number of n being the number of atoms in the system. Everything is interacting with everything, so that becomes very, very expensive. So with the argument that many of these are dying very quickly, then people started to introduce the cutoff. Say, okay, I'm going to look at only 10 angstrom or 12 angstrom radius. And how to do this, I'll I'm going to come back to it when we look at the topology file. So, but for electrostatic, again, I mean, we use the same cutoff for both electrostatic van der Waals usually. For electrostatic, it was realized and recognized that this is not a very good approximation. And there has been development like PME, particle mesh eval, that allows you to calculate electrostatic forces without any cutoff. So that's the reason. Okay, so now, so as I pointed out, one of the approximations that we do in classical simulations is to, this one. This guy, do you want to have it there or? Oh, great. You can. Perfect. Thank you. So first of all, I mean, I have a lot of things to say on this slide. First of all, I think this is a good example of showing that all the bimolecular force field development, everything you see in CHARM, AMBER, GROMACS, and other things, you can actually get it all the way off, is based on the idea of fragments. Okay, so don't overdo, if you want to do your own molecular system, don't feel like, I have to include my entire tetrapeptide or my entire molecular system in one quantum mechanical calculation, because that's going to be the best representation. Everything is quantum mechanic, etc. No. So we are going to simulate a big protein, and in order to do that, I cannot develop parameters for that huge protein. So what I'm going to do, I'm going to just look at the fragments or pieces that compose that protein, in this case amino acids, and try to develop parameters for these simple moieties. So let me draw a amino acid. This is the backbone, and then you have the side chain here. So like I'm going to say, okay, I consider this side chain to be a separate fragment. So let's say I have a serine side chain that looks like this. So I'm going to use, looks like methanol, right? So it's found here. So if I replace this guy with a hydrogen, it becomes methanol. There are lots of experimental data on methanol. It's a liquid. I know the heat of vaporization. I know the density, everything. So I can develop my parameters for methanol, a fragment, a model compound, and then hope that when I put this methanol, it's connected here and connected to a backbone set of parameters in a protein, its name becomes serine, then everything that I've developed for this fragment hopefully also works within the larger compound. For the backbone, so I think backbone interactions are extremely important in proteins for your alpha helix formation, beta sheet, and everything for secondary structures. So I'm going to use another model compound that looks like this guy. So let's say simplest model compound I can think of is something like that. Just cap the two ends with hydrogens. So what is this? Cetamide? No, cetamide has the nitrogen on the other side. So maybe actually I use that because it's going to be in the peptide. But the point is I'm going to use a small molecule, and then for this one I'm going to do quantum mechanical calculations, calculating the charges on each point here, and then the bond parameters and everything for this model compound, because I can handle that quantum mechanically. And very likely there are experimental data also for this compound that allows me to fit my parameters to get the right physical-chemical properties for that compound, and then I'm going to transfer them to the larger molecular system that I'm going to use. So this idea of transferability is very important in the basic concept that we are doing. So if you want to do the same thing for your molecular system, just keep that in mind. So like, I don't know, you might have, let's say, something like this coming down here. Just something like this. Then instead of calculating the entire thing, so I know that these two electronic systems are isolated. There is no conjugation between them. So maybe I can cut this here do quantum mechanical calculations for this fragment separately, and then for this fragment, and then put them together, because that's what has happened in the rest of the course. So you keep this in mind. So fragment-based calculation. So now, the other thing that I have to say on this slide, so this is an example of, let's say, an amino backbone in the NH group connected to maybe two methyl groups, dimethyl amine. And then I can have an example of a carbonyl group in the backbone. I can put maybe two methyl groups here to have acetone here, representing the carbonyl backbone. So now I have to specify some charges for my electrostatic interactions. I need to have these two guys. So where are they coming from? What is the philosophy? What are they supposed to do? There are different philosophies in charge fitting. It's quite different in charm and amber. So these are two examples of biomolecular force fields that are used. So in charm, the idea was, okay, so I'm going to use these charges on this molecular species to reproduce its interaction with the environment. Yes?
Yeah, I think this calculation of partial charge is chemically dependent and environment dependent.
Absolutely.
So this calculation of partial charge is it include a solvation effect or something like that?
Include what?
Include the water or something else. So how to calculate the partial?
Wait 5 minutes, then we talk again. Okay, so this is the most problematic part of the force field, and people are trying to take care of. But again, the point is, you need to have two charges here, the most representative charges that you can. So in charm, they argued, okay, these guys are supposed to interact with the environment. So now you're talking about the solvent, and that was also what they thought would be the most representative form of the environment. So what is the most representative thing that I'm going to interact with? Is it a protein side chain? Is it an ion? Is it water? And they argued that water seems to be the solvent of life and everywhere. So let's look at the interaction with water between this guy. So we can do that quantum mechanically very accurate and place it, look at the distance and the angle and calculate the potential energy for that interaction. And then we try to come up with charges that reproduce that potential energy. Quantum mechanical interaction with water. But then, of course, the problem is, as we know, so let's say if you place, a sodium ion here, so these are those charges that come from interaction with water. We start with molecular charges. This is something as some sort of population analysis in quantum mechanical calculations, and try to optimize them, modify them, so that you can get the interaction of this guy. Let me put hydrogens for now, doesn't matter, with water. And this water is a special water. It's the charm water, tip-free. Okay, it cannot be anything else, because I have to fit the potential. For quantum mechanical part, it's a real water. But then when you come to your classical part, you have to have a fixed reference here. So you have a water that has 0.8 positive charge here, and 0.8 negative charge here, 0.4 on each hydrogen. So I fix these and try to optimize the charges on the other part to get the interaction rate. So that's the argument. But of course, we know if you put a sodium here, you're going to get a lot of more electrons here. It becomes, I don't know, minus 0.7. This might become plus 0.7. So this is going to be polarized by the environment. If you put it in the protein, if it's this part of the protein, goes back to your dielectric question also. You have a strong electrostatic potential here, weaker there. So this is, yeah, of course, this is a very, very crude approximation, but what else can I do? So you tell me what is the most representative form of the environment. I cannot, I shouldn't say I cannot. In most programs that we use, these are fixed throughout the simulation. So now there are new approaches in which you talk about polarizable force fields that allow you to some degree to deal with this significant problem. So now instead of having, let's say, one atom for my oxygen with a fixed charge. So I'm going to say, okay, so now the fixed charge and a fixed mass. I'm going to say, okay, so now I'm going to break this total mass. So I'm going to reduce this mass a little bit and introduce a tiny little guy here, M. And I'm going to just, this total charge that I have here, maybe I do it somehow and put this charge here on this little guy. And instead of having 1 point representation, now I have 2 point representation. And this guy gives me a dipole that can react to the field coming from the environment, so it can move. Becomes your calculation. Your calculation becomes more expensive, but at least you have some polarization effect included. And there are some tricks that you have to do. This is a very low mass object. It becomes even worse than hydrogens, that's for which you had to use 1 femtosecond time step because they move too fast. Now for this, you have to somehow make sure that this doesn't become a problem by fixing this or cooling it off very strongly. You can do those tricks to get it to work. But I mean, this is, again, one way of including polarization effect because we are stuck with a very rigid way of defining these things. You have a question about this particular part or the general idea? Then wait. So now, for Amber, they had a different philosophy. They said, okay, well, I mean, Peter Gorman started that path, and their argument was, okay, I have this molecular system. The only thing I need to is that this guy, right here. So I want to have a set of charges on these points here. That's what I'm doing on these atoms here. That would reproduce the electrostatic potential, something a little bit more real that you can calculate quantum mechanically on the surface of this molecule, because that's where it is interacting with other things. It could be water, it could be protein, or whatever. That's fine. So if I can reproduce electrostatic potential on the surface, then I should be fine, because the other species feels that electrostatic potential right there. And I can calculate the electrostatic potential directly from my quantum mechanical calculation because I have the densities and everything. So I put a set of charges that will produce that value, and everything else coming in feels exactly the same. So that makes it easier to set up. So the placement of water next to these groups in this example doesn't look like something difficult, but if you have a complicated molecular system trying to add water individually to these points, it becomes very tedious. Sometimes it doesn't work. Sometimes it tries to establish two connections with two parts of the molecular system. It becomes very difficult. Sometimes actually in papers you even see that people say, I mean, I didn't use it because it was difficult. So this electrostatic potential fitted or restrained electrostatic potential fitted charges is the philosophy of Amber. It's a little bit easier to do. And it has a different philosophy. So now, if you are working with Amber, you should try to, that's general in all force field development. Whatever you are doing, try to be consistent with the rest of the force field. So, because otherwise you are doing something very different from the rest of the parameter set that you are using, and you don't know what might happen. So you might, if you go back to the charm way of doing things, they are using a particular level of theory for calculating these charges. Nowadays, we can do much, much better, much higher levels of theory, much larger basis set, but again, you're becoming consistent with the rest of the force. They are using a cutoff of 10 or 12 to adjust and finalize the parameter set. So nowadays, maybe you say, oh, I can easily do a cutoff of 15. Sure, I can do it. That's going to be a little bit more expensive, but I have the computer time to do that. And but you should not do that, because then you're going to introduce imbalance in the force field. And these new cutoffs that you are going to use have not been tested. We don't know what happens to the protein using that cutoff and the parameters. So you have to try to be as consistent as you can. As I pointed out, for charm, it's a little bit difficult to do these things. That was one of the reasons that we developed FFTK, force field toolkit, to sort of streamline some of these tedious steps. And you will hear about that in the last part of today's talks. So we're going to help a little bit to place this, to generate all the Gaussian files you need. Then you get actually all the output files and derive all these numbers from the Gaussian output files and try to do all the filling and everything. But it still can be problematic. So now, if you're writing a paper with charm, so you can say that you have to tell the reviewers and the reader that if you are aware that you were supposed to do water-based parametrization, but because of technical difficulties, you couldn't do it, or you decided not to do it. If you declare that, then people accept that, okay, so you knew what you were doing, and you are providing justification why you didn't do it this way, and you decided to use the easier electrostatic potential kind of charges. So that's important. Back to the conformational sort of sensitivity of these charges. So that's another issue that is very difficult to capture, because all of these charges, I told you, we are going to use a model compound to derive these charges. So now let's say I have a model compound that for a particular problem, let's say I need to use this nitrogen here, trying to, yes. Oh, sorry, maybe I should write. Okay, so now let's say I have a molecular system like this. So now I would like to use this fragment as a model compound and derive charges. But of course, depending on the conformation that I use here, this might have different conformations. So right here, so let's say if the nitrogen is down here, you might calculate a different set of charges. If this bond rotates and you have your nitrogen up here, then you might have a different set of charges because it's now closer to oxygen. So whether you use this one or this one, for the conformation that you feed into your QM calculation, quantum mechanical calculation, you get a different set of charges. What are you going to do? So that is a problem for this approach and that approach. Doesn't matter what, because we know conformation. That's one kind of polarization, right? So you move up more electrons here, you are not going to become more positive. So that's a problem. So even for this guy, let's say methyl groups. So for methyl groups, for example, we know that this guy is going to rotate easily. So you have 3 hydrogens that are going to be, during your simulation, identical in terms of charges. You have to treat them the same because they have the same type, atom type, right? So it's the same kind of chemistry because this is freely rotating. I have to symmetrize interactions here. But if you calculate the charges, look at your output file from Gaussian, this guy, because it's closer to this nitrogen, maybe it is becoming a little bit more negative, and the other guys are going to become more positive because of the different environment they have. So we have to symmetrize them because I can't start with let's say, a negative point here, a positive point here. In my quantum mechanical calculation, it stays that way, but when I put it in the MD simulation, this thing starts to rotate freely, and then at some point you will have negative charge there, completely wrong description of the charge distribution. So this becomes really hard, and I think that this is indicating or signifying the problem of representing a complex electronic structure with a few points with fixed charges in a space and a bunch of parameters. So that's really a major shortcoming in classical description of biomolecular systems or molecular systems in general. But again, if we don't do these approximations, we won't be able to do longer simulations that we would like to do. So trade-off between accuracy and sampling. So now, questions. Those 2 questions that you guys have.
So if we make the model whatever you want and put in AMI, then optimize the structure fundamentally, then find the partial charge. Then this partial charge is both for geometry calculation or not?
So give me an example. It depends. So I can, let's say you want to put, instead of calculating this separator, put it in a water box.
Or water box, or maybe
Okay.
some ion.
Or in the presence of an ion, okay.
Right. Then optimize it fundamentally. Then find the partial charge.
Sure. So again, you see, we are trying to have here, what they are trying to do is to have as general as possible set of forces, something that works with everything. So that's their difficulty. But if you have some specific examples, let's say for here, so I know in my binding pocket, so let's say this thing is a drug, and I know that it's going to sit in the binding pocket, and I see that from the crystal structure that this is the conformation. Then I know very specific kind of arrangement for which I have to have the best charges. So I don't have to worry about this conformation of flexibility and everything. I just use this one for the QM calculation, maybe even actually including something from the protein that might polarize the system. I get the best set of charges possible. For your example, let's say you are interested in the carbonyl group, and you say, oh, I know that in my classical simulation, this carbon is going to interact with the sodium ion because that's the most important configuration I want to look at. So yes, I would take this as my QM region, calculate the charges here, taking into account the polarization, the strong polarization I have. This becomes my model compound. And then just take this and put it in the rest of the classical system. Sure. But again, if you don't know what's going to happen to the sodium or this carbon is going to move around, so let's say at some point this sodium leaves, now you are left with a wrong kind of negative or very highly polarized carbonyl group in the absence of sodium that does something really weird. It's a very non-physical. That's really the problem. So if you know your ligand, so I think one of I already mentioned, so if you know any particular or specific aspects of the configuration that you are interested in, you can actually use that as the main representation of your molecular system.
We are using fragment-based method, for example, for the peptide. So if we join peptides like that, what happens to the partial charge of linking peptide?
At the linking region. So there is, you have to fix it. You have to, because again, so if you're talking about, let's say, so here, right? At the peptide bond. So what happens if you use a fragment? So right now, the force field, what is happening is that there is no charge transfer here. This bond, this is a separate group. I think this guy is a separate group. This one is a separate group. This one is a separate charge group, and that is a separate charge. There is no charge transfer. So right now, that's what we have in the force field. See, this is a neutral 0.5 and 0.50 charge on this moiety. That's a separate charge group. And nitrogen, hydrogen here that they have together with C alpha would balance this to a 0 charge group. So there is no charge transfer.
How we manage the partial double bond nature of the peptide?
Partial double bond. Oh, so what is it? What is it that you want to represent in a partial double bond?
How does that affect the charge? Because this one is with the...
That's yes. So we are talking about this bond now here. So there is no charge transfer across this bond. But this bond, instead of being a single bond, you can actually treat it as a partial double bond, maybe by having a higher force constant, sort of shorter double bond. And another thing that we're going to do is going to have an improper dihedral angle for, this is an sp2 center, we know that, but also for this nitrogen, you keep it planar because of this partial double bond nature of that one. These are the two things that you can do. But as far as partial charges is concerned, there is no treatment. So this hydrogen is also polar. So you can see this has a significant charge that can form a hydrogen bond. That to some degree also takes into account. But that's it. Yes?
So if you wanted to use a different water model than tip 3, can you still use like amber, or do you have to use something completely different than charm and amber?
If you want to use a different water model, you cannot use charm. Absolutely. So the tip 3P is a bad water as far as diffusion constant is concerned, for example. In fact, there is no water model that gives you everything. Even for a 3-atom system, 1 oxygen and 2 hydrogens, there are, I don't know, more than 100 different kinds of force field depending on what you want to represent. Is it the dielectric properties you want to get right? Is it diffusion? Is it density? Is it structure? So no single parameter set can give you everything. So one bad thing about tip 3P is the diffusion constant is twice as large. So it's 5 instead of 2. 5 times 10 to the minus 6 centimeters squared per second. So in some, I remember actually at one point I wanted to use a better water model that has the right diffusion constant because we wanted to calculate permeability of water, but then very soon we realized that we can't, because if you do that, all the interactions between the protein and your water model is going to be wrong because you're not using the right water model. Absolutely. So you should use the water model that, especially for charm, because they fit everything else to tip 3P. So especially for charm, you have to use tip 3P. For others, I think you can be flexible. Again, many amber, I don't know about Gromax, but I think they are using similar water models. But I think there you have more flexibility because they don't do this. So you're more flexible. You can use, if you're aware of this problem, you can test and see what happens if I use, I don't know, different water models here. But be aware that you're now working with an imbalanced force. You can just test something. I want to see what happens. Is it sensitive to the choice of parameters of water, or is it robust effect? Right. So it's going to be imbalanced. There's going to be inaccuracies in your simulation, but you can of course test these things. That's fine. Yeah. But actually, as soon as if I'm a referee and I see you use a different water than tip 3P with your charm calculation, I'm going to say, no, something is wrong. How can you do it? Send the paper back. Okay. Good. So that's again, that's a very significant part of the force field. These are again charge-charge interaction. If you have a ligand and you're looking at how it interacts with the binding pocket, these are the most important kind of interaction, the strongest part of the interaction. So it's very important to make sure that you get as good as you can the partial charges. So that's the most important part, for which it pays to repeat some of the quantum mechanical calculations. Okay, so let's go back, please. Thanks. All right, so going back to this, we talked about this potential energy function. So many of these things come from the geometry of the system. At every time point, the program calculates these things for you, or initially they come from your initial structure. So we have a lot of parameters that we need to provide, and they come from different files. So this comes initially from their PDB file. These charges are in the PSF file in charm language. In other programs, they might do it differently. And then the parameters, most of the other parameters come from parameter file that you specify in your configuration file. Here's my PDB, here's my PSF that I generated using PSFGen. And then to generate that, you need to have the topology file, to have all the structure information in there, and then of course the parameter file that is needed to calculate the energies and the forces. So let's look at actually, I mean, I know that some of you are familiar with this, but let's look at these files quickly. So this is a structure of a PDB file, really something that is outdated, so it doesn't work. It's very limited, it's very rigid, and many people are moving from these PDB files. So it's a fixed format, kind of ASCII file. You can edit and revise this, but you have to make sure that you stay with the same column numbers. Like the first one is index, and this guy has to be at 11 and 12 columns. If you change this, you have to make sure. And no program actually uses these indices anymore because they're useless and they are so limited. Right? VMD generates its own, the PSF we generate our own indices, and so forget about this. So we have the atom names for each atom. Each line is one atom, so it has a name, and this name has to be unique within every residue. So in Charm language, every unit is called a residue. Could be a protein residue because things are started with proteins, but the water molecule is also residue. A sodium ion is also residue. A lipid is a residue. Your heme is a residue. Everything is residue. So within each residue, which is specified here, this is res ID, residue ID 3. You have to have unique atom names. If you're putting together your own molecule, then you can define it as a residue or 2 or 3. And within each residue, you need to have unique names, right? This is like the street, and these are the house numbers. You can't have 2 houses with number 1 on them or number 2. So these have to be unique. You can be created here to use atom names that you can use later for your analysis when you go to VMD and say name, blah, 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 and chain, whatever. So this is what you use to do your analysis. Then we have the res name, the same thing, res name for alanine, serine, tryptophan, whatever. Chain, this is the chain column. Res ID, these are the original res ID of the protein. You can rearrange them, you can redo this, but again, every residue has to have a unique res ID within each segment. So these are things that you did in PSFGen. You're generating these segments. Each segment has a number of residues, and each residue has a number of atoms. Then we have XYZ coordinates that we definitely need for our MD. And there are 2 columns here, the B factor and occupancy, that we don't use in our calculation most of the time, but you can use these to flag particular atoms, to fix them, to constrain them, to do other things with them. So you can use this. You put charges here and then show it in VMD, so you can use this as additional information for your atoms. So that's pretty simple. So now I'd like to So everybody sees from the back? Okay, so that's the PDB we were looking at. This is actually the system that we have in our tutorial. Ubiquitin in a water box. That's U is used as a segment name, XYZ coordinate, residue 1, residue 2, etc., etc. Nothing special here. And then after the protein, at some point you go down, you start defining your water box. Great. Okay, so water is defined the same way. So we have segments of water. So if you have a huge water box, you need to have multiple segments. That's another limitation of PDB format because it doesn't allow you more than a particular number of residues in each segment. So it's 9,000.
If you were working out to actually increase the number of segments in residue per segment.
Yeah, it's actually limited by the number of columns assigned to the res ID. So you can't, if you have, let's say, 100,000 water molecules, you can't put it in one segment because there is not enough room to say res ID 100,000. So because of that, they have to break it into WT 1, 2, 3, and so on and so forth. Every water is you see, is a residue. This is residue type 3, has 3 atoms, OH2, H1, H2. And this is residue number 5, residue number 7, 8. You know why they are not consecutive here? Why it doesn't start with 1 and then 2? This is the water box you generated. How many did the ubiquity example? Okay. So anyway, so you start with a protein, you throw it in a water box, and then you remove some water molecules that are overlapping with your protein. And your original water box is clean and nice, has 1, 2, 3, everything, but then when you remove some of the water molecules, then you lose those. And the program is supposed to keep the original res IDs, because for the case of a protein, when they say tryptophan 207, it has to stay 207 for the rest of your calculation. You should not change the original res ID for a protein because it has a biological meaning. So the same thing is applies here. You cannot save the res ID of this. So that's from the original file. Now, VMD has its own residue, not res ID, the whole residue. Residue numbering, everything in VMD has its own residue numbering. And that's how you can say same residue as whatever. So that's goes up there. But that's a different history. So nothing special in the protein data bank. So there's a bunch of residues and atom names and their positions. So what is clearly missing is the connectivity, what is connected to what, how many bonds I have, how many angles I have, how many dihedral angles I have, where are the charges. Those are things that I need to be able to do my calculations, my English equations. So they have to come from somewhere else. And that's
just an addition here, especially when you are working with charm, and charm is very creative in giving residues names. You cannot go beyond 4 characters for the residue name. So and if you look for VMD mailing list and MD mailing list, you will see this question coming over and over again. Every time that you see a residue name inside charm topologies, somehow you have to change that topology, that residue name to fit the 4 characters long name.
So if you want to call your drug, I don't know, ABC 350, you cannot do that. So you have to shorten the drug into something else. Oh, okay. Okay, so now in order to get the rest of the information, so now we're going to go to a topology file, see what is happening in the topology file. This is parameter. This is topology. So now in the PSFGen part of the tutorial, so what you need to do is to start with the PDB, and now I need to have some information. When I have a tryptophan, what does it mean? I just have the atom names. I don't know what is the connectivity. So that's the function of the topology. So for your drug, you have to define the topology of the system. For charm, Alexander McCarroll and his website, they have been maintaining the charm force field. So he's the main person who has been doing that. Oftentimes people develop parameters and topology for new drugs, new molecules. They deposit them there. So in case you want to do the same before going through this tedious process, you can check their so-called string file and see if other people have done this. So that's these files are maintained by him. And so every version of charm, we might have some addition because people go back and change these model compounds. They discovered that the initial approximation wasn't adequate. They have to include maybe larger model compounds or more molecular effects to get some properties. So we have different versions. This is specified here. Everything with exclamation mark is, of course, comments here. So we have a lot of comments here and lots of references. And then we start with the first part where you specify this is the beginning of introducing your atom types. So what are atom types? We had atom names. These are just house addresses. They don't have any meaning. But then atom types tell you whether it's a one-story house or a two-story house, or is it a palace or whatever. So it just specifies the nature of those atoms. So we specify these are the atom types. So we're going to use a lot of different hydrogen atom types. And here you're going to introduce their mass. And of course, for hydrogen, it's going to be 1 for all of them. But for any new atom type that you might introduce, so we have the atom type name and atom type number. So most programs use this. We use atom type name, but sometimes we might, or other programs might use atom type numbers. They have to be unique. You have a lot of carbons. Again, all of them have a mass of 12, but it tells you what kind of carbons these are. CT3 is aliphatic sp3 carbon for CH3, something that has 3 hydrogens. So if you have something like this in your molecular system, this is the atom type to assign. So we have all the atom types and their masses, nitrogens, oxygens. We even have a dummy atom here that has a mass of 0 here. You can introduce atom type here of iron, zinc, calcium. All right. For the lipid section, this particular one, if you look up there, it says topology file for all atom charm version 27 for protein and lipids. So from the name, we can also tell something actually about what is inside the file. But anyway, so after that, there are a bunch of things to declare. So all the commands in charm, if they are unique, they can be approximated to 4 letters. So these are declare commands here. They are declaring new atom names because we're going to need them. What is here is like we have Ca, which means C alpha. Here's an example of C alpha in alanine. But we're going to introduce a C alpha from the previous residue. We call it minus Ca. We're going to need it for connecting residues together because there are going to be bonded terms that go across multiple residues. So we need to have a Ca from the previous residue, the carbonyl carbon from the previous residue, the oxygen of the previous residue, and then nitrogen of the next residue, and so on and so forth. By default, the first residue in your segment, and everything started with proteins in charm. That was a original simulation that Martin Karplus did and he got the Nobel Prize lately. So everything is started with protein. Everything is protein-centric here. So we are assuming that every segment is a protein. So by default, they're going to patch the first residue. They're going to be patching it by something called N-terminal or N-ter, patching residue. And the last residue is going to be patched by something called C-ter, which actually I don't like. And I suggest to use neutral patches to cap your protein. Because for most of the proteins that we simulate, okay, let me actually talk about this when I come to these patches. Then you know what they are and what they mean, and you will understand this better. Okay, so by default we do that. So if you have a segment that is not a protein, you have to turn this off. You have to make sure that these patches are not applied. By default, that's going to happen. And automatically, angles and dihedral angles are generated automatically. You don't have to specify them. You just specify bonds, and the program, the PSFGen in this case, knows that it can generate all the possible angles and dihedral angles based on the connectivity that you program. So these are some general rules. And then now we start with blocks that are called residues. So now your new drug, your modified residue, your new inhibitor, whatever you want to simulate, your new solvent you want to simulate, it's going to take its own block. So we call it a residue. Again, everything is residue. That's the name of the residue, alanine, and it's the total charge of the residue, 0. So then we have the concept of these groups. So charged groups, or charge groups, I should say. And I'll explain what they are. So ignore them for now. Then we have atom lines. This one is the atom name. That's the same thing you have in your PDB. It has to be, or otherwise the program is confused. You have the atom types. Now you are assigning atom type to each atom name, and we are assigning partial atomic charges to this atom. So here you have the structure of the residue drawn after this exclamation points here, marks here. So you can see where these atoms are located in your alanine residue, which you may see it has open ends, right? That's why in the beginning and at the end, we have to cap them. Okay, nitrogen is there. Nitrogen is connected to sort of HN is the hydrogen connected to the nitrogen, has an atom type H. It's a polar hydrogen and has a charge of 0.31. And this goes on and on. C alpha, hydrogen connected to C alpha. And then we have C beta, which is a CT3 atom type. And if there are 3 hydrogens connected to it, they have unique names, HB1, HB2, HB3, but they have exactly the same atom type as they should because they are identical chemically speaking. And their charges should be symmetrized. So that's what you need to do again if you are defining your own. If you want to change a charge on, let's say, for some experiment, you want to change the charges on all the methyl groups in alanines throughout your protein. Then you can come here and play with this part. We change these charges, and then apply PSFG. Now all of your alanines will be using a different set of charges, for example. If you want to make some masses very large, but remember, this is going to be applied to all the alanine, all those residues in your molecular system. You can go up and sort of change the mass of one of the carbons, make it 10 times larger. Or you introduce a new atom type yourself and give it a mass that is very large, and then use that atom type in your special residue that you want to investigate. Okay, so far so good. So as you can see, the carbonyl of the backbone is defined as a separate charge group, and the nitrogen and C alpha are used as a separate charge group. Okay, so now what are these charge groups? So again, we talked about the concept of cutoff. So instead of calculating all pair interactions, I can't do that. I'm going to define a cutoff and say this atom will be only affected by residues within a particular R cutoff distance, 10 to 12 angstrom, depending on how you look at it. So I'm going to only include atoms that are within this radius in my non-bonded interaction, my charge-charge interaction, for example. So if you do that, again, for some groups that are completely inside, whether you include them or not include them, so that's fine. But imagine that you have a dipole sitting right at this boundary. So let's say you have a positive charge here and a negative charge here at a distance of I don't know, 12 angstroms. So this dipole, in reality, the interaction of a dipole with a charge is pretty weak, like 1 over r squared. But now, if because of the cutoff calculation or the way you are defining, you say, oh, that atom should not be included, this atom should be included, now you're introducing a monopole here, so much stronger interaction artificially if you just cut everything like that. So in order to avoid that, you're going to say, oh, well, I'm going to define these two guys as one charge group. So if one of them is included, the rest of the group should be included in the electrostatic calculation. So that way you're going to avoid this kind of boundary effects. So that's how you define these charge groups. So you define actually this as one group here. This is another group. You see the carbonyl group is defined as a separate charge group, and that was why I was talking about not having any charge transfer between. So now in NAMD, by default, everything is, the cutoff is applied on a residue-based basis. Even if you have one atom from the residue included, the entire residue will be included. But you can switch that to a group-based cutoff. calculation, and you might want to use that for your particular drug or molecule. Because again, if you, let's say, imagine that you have a the whole idea is to make the simulation faster. If you have a very long sort of residue, you might be able to break it into a few pieces, and you don't feel like you should include the entire thing in your electrostatic calculation only because a couple of atoms are within the cutoff distance. So you might take advantage of this to make that calculation faster. So this, the way it works is that every 10, 20, you can specify that. Time steps is going to update the neighboring list, so it knows what residues are within the cutoff distance, what atoms are within the cutoff distance, and then within 20 femtosecond or so, nothing is going to change significantly. Your approximation is fine, and then 20 femtosecond later, things might start to move in or out. You update the neighbor list, and then you know what atoms you should look at for your next step. Okay, so that's the definition of those groups. Okay, so again, if you want to use your own drug or ligand, you have to develop this, otherwise you can't do this calculation. The next step is the bonds. So these are a bunch of pairs or atom pairs based on the definitions of the atom names you have here. C beta is connected to C alpha, right? Nitrogen is connected to HN in no particular order. Nitrogen is also connected to C alpha. So here we're going to introduce all the bonds in the molecular system. Carbonyl carbon is connected to C alpha. Carbonyl carbon is going to also connect to the next nitrogen, the next amino acid. That's why we needed this plus N here. And we only need to connect it to one end, because if every residue is connected to the next, then the entire polypeptide is connected. You don't have to worry about the other ends. Otherwise, you will be doubly defining the connectivity. So all the bonds are defined here. For historical reasons, we have this command double, which used to specify double bonds, but right now, for the current version of the force field, this double and bond have exactly the same meaning. This is just another bond, CO. It is a double bond, but at the level of parameters, I'm going to specify a shorter double bond and a stronger spring constant to describe it as a double bond. There is nothing needs to be done otherwise. So now, again, we talked about, so bonds are defined here. Angles and dihedral angles, proper dihedral angles are specified automatically. That's it. Auto angles, dihed command we had up there. But then impropers are not done automatically. I have to specify those improper angles. So if there are special centers that you worry about their planarity or non-planarity, you can actually put them here. So you can see in this case, almost for every amino acid, you will have these two. So improper angles are specified by a center, and the three atoms connected to that center. Let's look at this one. Nitrogen is connected to the carbonyl atom from the previous. We are not introducing a bond here. We're just defining a center and how it should behave. This nitrogen is connected to the next previous carbonyl carbon from the previous residue, its own C alpha, and the hydrogen connected to it. So these are the three atoms connected to this nitrogen, and that's going to be, now we are going to introduce a force field parameter for this to keep it planar or in a pyramid-like shape or whatever you want. So that's one center. The other center is obviously the carbon. This guy is connected to its own oxygen, C alpha, and the next nitrogen, and these are the three atoms that are specified. So some of the side chains have additional sp2 centers. You will see more impropers for those side chains. So we are done by this point. Yes?
So the improper is like a fixed atoms groups in the simulation.
The improper, I couldn't hear.
So the improper is the peptide bond. It is planar, so we are fixing it as with two groups from the previous one and the next one for the planarity.
So we are trying to keep this center planar. All the three bonds connected to this to stay in a plane, that they don't do too much out of plane vibration. That's what we're trying.
Because if you calculate pi size, then you can calculate with respect to the plane, right? Moving.
So if you don't have these impropers, that center goes too much out of plane. We know that from vibrational spectroscopy. In order to fix that, we're going to use this additional. It's not a periodic function. It's a harmonic potential that keeps that improper close to its natural.
My question is, how much is the force?
How much?
By default applied to maintain?
I don't know the force constant. We can go and look at what the force constant is. I would guess in a few to 10 kcal per mole per should be radian.
So when we fix the force constant, so if you put 2 kilocalorie, 5 or 10, the fixing constant is the same. But even though we use a smaller number, there is a little perturbation in the angle, right?
It's a little perturbation in
the angle, right? So it's not fixed completely.
It's not frozen.
No, yeah, of course. Oh, yeah, by fixing, absolutely. No, of course. It's going to be a harmonic potential, let's say, allowing this plane to still play up in and out, right? But we are going to limit that to some degree because otherwise it's going to do this too much. So we wanted this to be like that. So I think there are even ways to get this from spectroscopy out of plane motion. But yeah, so we're not fixing them, if that's the question.
So why I'm asking is, if I want to design a molecule of my choice, then I'm defining the improper. So I can do it here, or else I can do it in a flat, like a fixed atom. So I can vary
fix atoms. I mean, when you fix an atom, you're going to fix it in space. If you constrain an atom, you're going to constrain it in a way. I mean, like you can constrain it with respect to its position. You can constrain it in terms of its bonds to neighboring atoms. So but I don't know how you would control the sort of out-of-plane motion of an atom with a set of constraints.
Fixing a dihedral, right? It's similar to fixing a dihedral. Fixing a dihedral, the 4 atoms are there.
So how would you fix a dihedral angle?
Define 4 atoms and
you define a potential. I mean, in that case, yeah, you define a potential and you want so that's to be not going anywhere. So yeah.
There I can control the force constant, right? I can see how the simulation goes. I can vary from smaller to higher number.
Okay.
So like that, I need to fix it, or by default, if I give it in the flag, it takes a particular value. That's my question.
I mean, you can do this yourself if you want, but people have done it for us based on real nice experimental data. Why do we need to do it ourselves? For your own molecules? Sure, yeah, I see, and I understand, okay. So if you don't have this information for your own molecule and you want to use other tricks to essentially do, yeah, I guess you can, yes, I agree. So, but just remember, dihedral is a cosine function. This is not. That's the major difference, so, right? So, okay. Yes?
So that's the order minus?
Say it again?
That's the order minus?
The order here?
No, the improper?
Yeah. Oh, what atoms? For this case, no, it doesn't matter because you are trying to keep it planar. But actually, when you are trying to keep it as a pyramid, non-planar form, that's actually a good question. I think the question, because I think in a dihedral angle, it's clear how the two planes are defined. So you have so you have the 4 atoms here. The first plane is going to be the first 3 atoms. The second plane is going to be the last 3 atoms. That's clear. But then you have an improper angle. So now you have 3 atoms connected to one center. So now you can have 3 planes here. So one plane formed by these 3, one plane formed by these 3, and one plane formed by these 3. So the dihedral that we are looking could be the angle between 2 of these 3 planes. And honestly, I don't know.
If I'm not wrong, the first atom in Improper is always the center.
That's true, yeah. But I think she's asking about the last.
The rest of
Yes. Yeah, the first atom is always the center, but the other ones, I don't know. We can actually maybe look it up after. Oh, we still have a break. Okay, so
This will come as an improper angle, right? Not the torsion. Take three and make combinations with it.
It's not a torsion, but it's an angle between two of these planes. You get the normal to those two planes, and then calculate that. So you have three possible. Right? Okay, so then the rest is something that looks very intimidating. You have to do this for all the atoms in your new drug with, I don't know, 65 atoms, but you really don't need it. So what's in here? Oh, first of all, this donor and acceptor terms, they go back to very old versions of the charm force field in which you had to specify hydrogen bond donors and acceptors. Explicitly, they had explicit terms for hydrogen bonds, but I think after charm 19, everything includes, doesn't include explicit terms for hydrogen bonds. Hydrogen bonds are essentially described based on the partial charges of the molecular system. You have a carbonyl, a negative oxygen here, and a polar hydrogen, that they would attract each other. That gives you a little bit of the geometry of the hydrogen bond as well. But so you don't need this. So we can ignore them. They are there for sort of back compatibility of the topology. So now this IC table, or internal coordinate table. So here you can see a set of 4 atoms and 5 numbers. And these numbers are sort of formatted nicely to include a lot of information in a single line. So like you have a distance between the first 2 atoms here. These are a standard geometry. Let's say if you have a perfect alanine with perfect trans and perfect single bond and double bond, you would have this geometry if you want to draw it by a molecular editor. So the bond distance between the first 2 atoms is here. The angle formed by the 3 atoms is here. And then you have the dihedral angle or improper dihedral angle formed by the 4 atoms. If you have a star, it's an improper. Then you have the angle formed by the last 3 atoms and the distance formed by the last 2 atoms. So essentially you have 5 internal coordinate information that allows you to construct the atomic structure of the system if you don't have it. So if you have your molecular structure, you don't have to worry about it. So this is used by some programs to build the position of missing atoms. You might not see it in the PDB, you have only the backbone, but applying this internal coordinates, you can build the rest of the molecular structure to have a complete residue. So you don't have to do it these days. You either have your ligand structure from the crystal structure, or you can easily build it somewhere else and just plug it in. You don't have to worry about this. I'm going to look at one more residue, and then we can have a break. So we'll go from the most boring residue, alanine, to the most interesting residue, arginine. Shortest to longest. For some reason, nature has decided to have basic side chains to be very long. I still don't know why. Maybe there is a biochemical reason for that. If everybody knows, please let us know. But arginine and lysine are the longest side chains we have. So arginine is shown here. So now residue is called ARG. It should match what you have in the PDB. Total charge of the residue is 1 because it has a very high pKa. It's almost always charged. And then you have the groups here. So the same backbone groups. You see, this is exactly what you had in alanine, the first 4 atom, because it's down here. And as I told you, everything in charm and other forces are fragment-based. We have figured out how this fragment should be. Oh, that fragment up there. And put it there with the same atom type, same charges. And then you go, the carbonyl is going to be defined at the end. So now we're going to go into the side chain. C beta and the 2 atoms connected to it are defined as one charge group, C gamma. The naming makes sense, CG, C gamma, C delta. and the hydrogens connected to it. Now you see actually CD and N epsilon and C zeta, they're all in one charge group because there is a lot of charge transfer between this positive center here and the neighboring carbon. So you are going to include C delta in the charge positive end, the guanidinium group, which we know is charged. So these things, I mean, usually charge groups add up to a neutral or an integer charge. So here you can see that it's 0, here you have 0, here you have 0, and now this long thing here carries the positive charge, and you can see how it's sort of distributed between different atoms. Then at the end, you have the carbonyl group of the backbone, which again sort of balances out. You have just a simple diagram. So one more thing that I forgot to mention is that all nonpolar hydrogens, and don't ask me why, all nonpolar hydrogens have a charge of 0.09. If you have polar hydrogens, you have to be careful. You have to make sure that you get their charges right. I'm trying to find some polar hydrogens here. These are connected to the one of the nitrogens, carry a lot of charges, form hydrogen bonds, but all nonpolar hydrogens have this standard of 0.09. That's a convention. Okay. Yes?
Is there any list of all the charges that we should use for adding a force field?
Is there a list?
Yeah. Yeah, like if we want to use it to build an inorganic.
Okay. So if you want to build your own ligand, yeah, sure. I mean, again, so we will get to that point later. So the idea is that one idea is to adopt similar charges. So you have to look at these atom types. They are defined a little bit there. So when we look at the masses, you see it says NP is a proline ring, NH2 plus, N-terminal, tryptophan, and in this ring, guanidinium, nitrogen. So you see you have some options here in terms of what atom types, what kind of molecular environment we are talking about, what kind of nitrogens these are. Is one of these similar to my own molecular system? Then you can simply adapt this atom type. If it's very special, then you have to give it its own new atom type and get the charges from your quantum mechanical calculations, however you want. Just put it there. So that's how. So that was arginine, and again, so the same thing. You define all the bonds in the molecular system. What is connected to what? It's being connected to the next nitrogen, and then we have more improper. Two of them are for the backbone, similar to alanine, but then we also have the C zeta, the carbon in the middle of the three nitrogens, and all the partial bonds we have there makes that group as sort of plain. Group for which we define improper, donor acceptor we can ignore, and there is a long isotable. Yeah. All the information, topology information for different residues. I think the rest is not too complicated. So one thing is about charged or acidic residues. So for aspartate and glutamate specifically, and histidine becomes actually a special case. So these are acidic residues. They have pKa values that can be modified depending on the environment. So you might have to consider different protonation state of these residues. So for aspartate, for aspartate and glutamate, these are the two special cases of acidic residues. So you are dealing with a carboxylic acid group that can be protonated and deprotonated. So you have the protonation, deprotonation reaction, and then the pKa or pKa of this reaction. So it's for these guys it's about 4. So now you have to decide for a free glutamate or carboxy group or free aspartate and glutamate in solution. You can actually use this pKa value, the difference between pKa4 and pH7, at which you usually simulate the system is 3. So that means you have 3 orders of magnitude difference in terms of concentration of the protonated form versus deprotonated form. That's an easy decision to make. But when you put these groups inside the protein, because of the local environment, these pKa's can be shifted significantly. So what are you going to do? This is another problem with fixed charge representation of the system. So at the beginning of your simulation, you have to decide whether you want to use a neutral acid or you want to use a deprotonated acid, a charged acid, and that's going to continue to be the case for the rest of your simulation. It's better to make a good decision. So there are some pKa calculation programs. So one of them is called pKa, like this, that there are H++ and other pKa estimators, I should say, that look at these individual residues within a protein context, and based on the local environment, they decide, and some of the Carver algorithm sort of randomly protonating, deprotonating these things, they decide what would be the most favored, sort of energetically most favored species. And based on that, they make a suggestion. They tell you, oh, we think, well, 90% of your glutamate and aspartates have pKa's that are pretty close to their solution values. Nothing special is happening. But you might find a handful of residues that have shifted pKa's. So, for example, you might have residues that have a pKa of 8. So as soon as your pKa goes higher than 7, at which you're simulating, then you have to change the protonation state of that residue, because it is suggested that this residue is going to be protonated within the protein environment. So I would look at those residues. These are just suggestions, so these are not very rigorous kind of calculations. It's kind of quick estimation, but it's very fast, and it looks at everywhere inside your protein, something that you cannot do visually probably. So those suggested residues with shifted pK, I would look at them and see, does it make sense? Are there 2 acidic residues next to each other? Both of them cannot be negatively charged at the same time, for example. Does it make sense chemically? And examine them, and even you're happy with that suggestion, you can actually accept it and change those residues to protonated aspects. So by default, everything will be negatively charged. But then for those special residues that you have shifted pKa's, now you have to apply a patch to protonate them. So that's something that you should do in the beginning of your simulation. That pays off later, so it's a little bit more work in the beginning, but you're going to be sort of more confident about the choice of these protonation states. That's an electrostatic interaction. So you are talking about having or not having a charge right in the middle of your protein. So it can make a huge difference in terms of dynamics of your protein. So you have to do this step carefully. So aspartate, glutamates are not too bad. But then one thing that becomes even trickier is histidines. And histidines are so in the case of aspartate and glutamates, at least for the solution form, you have a pKa of 4, which is pretty far from 7. For aspartate, for histidine, the pKa value is 6.5. And then on top of that, you have 2 tautomers. So if you look at the side chain of histidine, so you have 2 nitrogens, double bond up here, and then you have, even for the neutral bond. So first of all, the pKa is 6.5, so which means at pH 7, so you have 1/3 of 1 tautomer, 1/3 of protonated form, charged form, and 2/3 not unprotonated form, neutral form. But even for the neutral form, you can have 2 tautomers. One is with the proton on this nitrogen, and then you have a double bond here. And the other one I'm trying to try with the blue, you will have a proton here with the double bond here. So these are the two tautomers. So you have the C alpha, C beta, C gamma. Then you have N delta, C delta, and N epsilon, C epsilon. So if the proton is here, you call it HSE. If the proton is here, you call it HSD. These are the two forms of neutral histidine. And then if you have a protonated form, and you can see this can be easily shifted by a little electric field in the protein. You can shift up this value to 7.5, at which you have to look at the protonated form of histidine. Then you have HSP, in which you have two protons. Both nitrogen have the proton, and you have a positive charge in there. So now if you look at your PDB, the only thing you see there is HIS, histidine. That's the residue name for PDB for histidine. But now here you have to decide whether I want to go HSD or HSE or even in some cases HSP. So histidine is the trickiest case. So first of all, we have to decide. I think HSD and HSE, both neutral forms, are similar. So because this ring in principle can easily rotate and you have enough flexibility not to worry about where to place the proton. Remember, one side with the proton becomes a hydrogen bond donor. The other side with the lone pair becomes a hydrogen bond acceptor. So depending on the environment, you can actually probably decide what might be a better configuration. On the surface, exposed to solution, it doesn't matter. But inside the protein, for buried histidines, you can select all the histidines with VMD. Just look at their local environment and see whether HSD makes more sense with the proton here, or HSE makes sense because you can form more nice hydrogen bonds to your environment. So like you might have an oxygen sitting here, available to form a hydrogen bond here, and down here you might have a polar hydrogen to interact with the lone pair. So in this case, I would use HSD. So those also make actually an important effect on the outcome of your simulation. So look at this carefully. And again, so histidines can be easily shifted. So you will have cases in which you have HSP. So that you have to change those residues to HSP. So you define an alias in your PSF gene and say, every time I have HIS, treat it as HSD or HSE, flip the coin, it doesn't matter. For most of the histidines. But then for a specific histidines that you have checked, you have to specify HSD for that particular histidine. In your PDB, you can change it to HSD. And for some of them that you know, if you're protonated, you have to use HSP. And then regenerate your PSF file for this one. So this PK calculation is something that you need to watch for. Okay, so I don't have much time. So again, let me just very briefly, so you read the information about your residues, protein residues, water, ion, lipids, and for each residue, you come to this topology file, get all the connectivity information, all the atom type information, all the charges from here, and dump them into a PSF file. So at the end, the only thing you have is the PSF and nothing else for as far as the structure information. So this is an example of the PSF file. So it starts with atoms. So now you can see we have, these are the list of atoms here. So now you start with a real index number. This is the segment name. This is the res ID for that residue. These are the residue names. You have the atom name and atom type and the charges and the masses. So everything is dumped into this place. You don't need the topology file anymore. This one, the only thing that is missing actually is the coordinates, the position of these, but those are going to come from the PDB. So a combination of PDB and PSF provides enough information for the molecular system. And you only need the parameters after this. So you can, again, if you want to modify individual atoms or individual residues, you better work with this file directly. So that's what you were asking. So if I want to change the mass of, let's say, SD in this particular residue, then I can come here and make this 320 very heavy sulfur atom, for example. Or you can change the charge here, for example, you can neutralize all the carbonyl groups for a particular part of your simulation system to neutralize the macro dipole of a helix, for example. So you can work nicely with this PSF file. Now you know where to find things to test. So we use this a lot actually too. So we have all the atom types and atoms listed here. So the next block is going to be about, now you have the water molecules here, and the next block is going to be about the bonds. So now all the bonds, so now that we have real index numbers, so I'm saying 5,117 bonds, if I have read them from topology and put them here in this form. One is connected to 5. One is also connected to 2. One is also connected to 3. One is also connected to 4. This is probably the N-terminus nitrogen connected to a bunch of hydrogens and other. So you have pairs of atoms bound to each other, and the information about those atoms is up there. So everything is here. The same for angles, the same for dihedral angles, the same for improper dihedral angles. So imagine I want to delete a bond artificially. I just come here, just you can delete this bond, and then that bond is going to be gone. Probably you should also delete the angle that includes that bond to have a more reasonable description. Well, you don't have to. You can remove any potential energy term from your calculation by just modifying some number. Or you can introduce a new bond here. So I want to introduce this. You have other ways of doing it in NAMD, but let's say I want to add a bond connecting the two ends of my protein. A bond that is 55 angstroms long. Completely artificial bond. So I just find out that atom 100 connected to atom 2500. I just add this pair here. And now there's a new term in my PSF for which NAMD wants to have the energy parameter. So of course you have to make sure that that type of bond exists in your parameter file. That's another line that you can add there. And then you have just this new type bond there.
So far we've been looking at like the visual bit, how they're defined in this file, and then they're connected to the residue before and after them. But why is sulfide bonds? Because then we have a residue from somewhere connected to residue from another part of the
no, that's the problem. I'm trying to be fast. In fact, I should talk about this because that's, so I'm going to be late for my next meeting. That's fine. So the patching. So once patching, I always call them post-translational modification. So like protein biosynthesis, you just polymerize it and then come in and do all this patching and changes. So the patching is every time you want to do little modifications to a particular residue. You don't want this to be applied to all the residues, but you have a specific sites where you want to form an SS bond, you want to cap a protein in the beginning and at the end. So you use this kind of residues. This is back to the topology file, by the way. We had the residues, and now we have patch residues. N-terminus. So N-terminus is a patch that we apply to the beginning of the protein. You saw every amino acid had only NH group on one end and CO on the other end. They have open valence associated. So what we do, we come in, you can change anything here. You can introduce new atoms. You can delete some of the old atoms. You can modify their atom types. You can modify their atom partial atomic charges in this patching command. So that's what is happening here. So you say, in PSFGen, you say, by default, you might remember, by default, this is going to be applied to the beginning of your segments. That was in the topology file. But you can also apply it separately too. So in this case, you say, apply this patch command to residue number 3, which is my N-terminus in this case, for example. So it's going to come in and replace that NH group we had here. It's going to remove that hydrogen, delete it, and add 3 new hydrogens here. It's going to modify the charges in a way that now you have a positive charge on this terminal amino group. So you can do the same thing to the C-terminus. And again, if you are dealing with the real N-terminus and C-terminus of your protein, okay, use this because real proteins have charges at their end. But almost for every system, unless there is something special, for every protein you are missing some big piece on the N terminus and on the C terminus. So meaning that what you have in your simulation is somewhere in the middle of the polypeptide chain that is not charged. So that's why I recommend to use neutral patches. There are neutral patches down there that do not introduce this extra positive charge somewhere that it shouldn't be. And for most cases, these are exposed to solution. It doesn't really matter, but I find neutral patches a better representation of a position right in the middle of the polypeptide chain. So they might cause. Glycine has a special patch because it has two hydrogens connected here, so it should be treated differently. This is proline the same. It has a different backbone. You need to apply a different kind of patch to it. This is a different patch for acetylated N-terminus. This is one example of neutral patch that you can apply. But back to the disulfide. And of course, you have the same thing with the C-terminus of the protein. So now here is a patch for the disulfide bond. So here in this case, you have, the only difference is that you are modifying two residues at the same time. So most of the other patches apply on one residue, but this one is acting on two residues. And the only difference you see here is you have these ones and twos representing the first residue and two residues. Everything else is the original atom names, right? So you say, for example, in this case, delete one of the hydrogens of the first residue, this hydrogen of the second residue, these are the SH hydrogens. And now you're going to introduce a new bond connecting these two sulfurs. So this is here, 1Sg is going to be connected to 2Sg. And then you have to do some of the adjustment of the charges and atom types because the chemical nature of this moiety is going to be different. One word of caution, when you are using the regular sort of topology file or regular residues, all the bonds and all the angles and dihedral angles are generated automatically, but after patching, they are not. So if you feel that you are introducing new angles now here, you have to do that explicitly in this section. So that's good. Okay, so you put everything in the PSF as we discussed. Again, you have the bonds, angles, dihedral angles also here. And then the last thing you need is just parameters. For every bond term, I'm going to need a force constant equilibrium value from somewhere. That for the program, for NAMD to calculate energy and forces. So they should come from the parameter file. So again, we are going to use atom types here. The chemical nature of these atoms are defined or specified by these atom types. So I'm going to use those atom types. And in the parameter file now, you can imagine I have all the information about the, let's say the first section is bonds. So it reminds you of the form of the potential and the units, kcal per mole per angstrom squared and angstrom. And then you have for every pair of atom types that might be bound together, you have the force constant and the equilibrium value. So if you introduce a new bond, the bond we talked about, 55 angstrom, the two ends of the protein, I can put two atom types called ET, my initials, force constant 600, and distance 55 angstrom. So that's where you have introduced a new bond to the system that you can use. So this list goes on and on. So again, that's the first part for the bonds. And then for the angles, again, you have three atoms in this case forming an angle, and then you have the force constant and the equilibrium value. So the first two numbers. This is a Urey-Bradley term. In case it is used in your potential, you can use it as well. And then for the dihedral angles, so now for the dihedral angles, the same thing. So you have now, in this case, you need three parameters, and they are defined for here. 4 atom types, and for each of them, I have the force constant, the periodicity, n, and the phase, these three values for each dihedral. So one thing special, a couple of things special for dihedral is that you can have multiple terms for the same set of atom types. That allows you to have really fancy forms of your potential, like a Fourier series almost. So that allows you to introduce really cool features in your potential. Maybe cis-trans isomerization, you can make one of them a little bit more stable than the other one and sort of add some modifications to it. So you can have multiple lines for the same set, whereas for angles and bonds, you cannot. And then the other thing is the concept of wildcards here. So sometimes you have X's. If your sort of dihedral form is not found explicitly here, you can see some examples. So if you have a dihedral form or a dihedral set of 4 atom types that is not introduced specifically up there, it's going to look at this wild card and see if the middle 2 atoms are C and C, is going to use this general form of the dihedral potential. And I'm going to give you one more warning about this, and then I'm going to switch to Chris's presentation. So here, just remember that, so the bond that you have here, let's say if you have a bond that is connected to 3 atoms on each end, so you will have a 3 by 3, 9 dihedral terms for this, right? So you cannot put all the barrier, portional barrier that you have for this on any single of these bonds. It has to be distributed in a way that the sum of these, all these 9 components, give you the overall barrier for that relation. So that's just something. These are defined redundantly, so there are lots of redundancy.